Hi, my name is Emily Mikowski, and today I'll be talking about the Crank-Nicolson method. And this is a method that you can use if you need to use a value of greater than 1/2 for R in the heat diffusivity equation. So first, I'm going to start by rewriting this, and you can rewrite it to be Tj to the n plus 1 minus Tjn over delta t, which, if you remember from the previous videos, n represents the time integer and j represents the position integer, and this is going to be equal. It's going to be equal to alpha over 2 because we're taking the average, and then we need to approximate the second derivative, so it'll be equal to parentheses tj plus 1 to the n plus 1 minus 2 tjn plus tjn minus 1 n plus 1 over delta x squared, and then this will be plus. I don't think I can fit it all down here, so I'm just gonna write it down here because I don't have room. But it'll be plus tj plus 1 to the n minus 2 tjn plus tjn minus 1 to the n all over delta x squared again. And then from here you can simplify by moving t over and then pulling out the delta x squared. So I'll do that here. J n plus 1 equals delta t squared, and then and then, so this right here is going to be your R. That'll be your R. And then this is going to be your next timestamp. And then this, and this is your previous timestamp. And then, so you can rewrite it. Oh, I couldn't finish it. So you rewrite it to have n plus 1 on one side and n all on the other side. So I'll do that. Equals n plus 2r n plus r minus 1. So this is going to be your most stable form because there's no restriction on the time to make for the heat to diffuse. So, and then, but you do have multiple unknowns, so you will have to use a matrix to solve it, and I can go through that part. Let me erase this because I don't have room. And then I will go through it further in the next part of this video too with the code, because the matrix is very complicated to solve, but I'll show the beginning of it. Very good at drawing this. Okay. So we're gonna have your negative bars here going throughout the matrix. Oops. And then, oops, that's why I made it. 1 plus 2r, 1 plus 2r, 1. 1 plus 2r, 1 plus 2r, 1 plus 2r. And then on here, this is j equals 1, j equals 2, and so on and so forth. And then the next one you're going to have, this will be your time. And this is where your initial conditions can come in to help you solve this, because you already have some of the values. So Tj equals 0. So when T of 0 is going to be your 350, because that's going to be your leftmost temperature, and then you're going to have Tj equals 99, which is going to be your rightmost, which will be your 450 Kelvin. Or 400, actually, sorry. And then you're going to rewrite this with your leftmost and your rightmost, which will be RT99. So that'll be your rightmost, and then your leftmost will be RT0, which is your leftmost. And in this one is going to be RT2 plus 1 minus 2r times T1 plus r times T0 plus r times T3 plus 1 minus 2r times T2 plus r T1. Okay. And then to find your final matrix, you're gonna multiply. Oh, I messed this up. I just realized that. No, I didn't. No, I didn't. Yeah, you're gonna multiply this and this, because you're only looking at your inside. You don't want to include. So, like, we can call this part A and this part B, but we're not looking at the endpoints, because the endpoints are going to be constant, because we already have those initial conditions. So you're going to do A times B to get your final matrix. And so this is also your rightmost and your leftmost. I think I said that earlier, but just to specify again. And then, yeah. So I will solve this, and we can visually see it on a graph to see if having an R value greater than 1/2 either stabilizes it or destabilizes it. So we'll see what that looks like in the next part of this video. Okay, so I will be using the Crank-Nicolson method to
prove that we can use a value greater than r, a value for r greater than 1/2, because in video number 2, if I used a value greater than that, then it caused stability issues. But using this method, we're able to use any value of r. So the first thing we're going to do again is import numpy. And then we're plotting again, so we need the subplots. So I'm going to import and from this plots. And then this time we're dealing with matrices, so we need to solve our tri-diagonal matrix. So we need to also have this here. Then that's all the stuff that we have to import. And then the same thing, this is going to be, NX is going to be your number of divisions in the bar. And then NT is going to be your timestamps, which we'll use 1,000. And then R, you can use any value greater than 0.5. Well, you can use any value, but I'm trying to prove that you can use a value greater than 0.5 and still have stability. So I'm going to just use 1 for right now. And then so then this creates your x-axis, and then create the y-axis. And then your initial temperature is still 300. So that's why that's in there. And then you still have the same conditions where one side of the bar is 350. Oh, oops. And then the other side of the bar is 100. Okay. And then we're going to be using, oh, no. And then we're going to be declaring the abandoned matrix. So we're going to say A equals MP dot zeros, and then 3 is the number of rows, and then we're going to have NX minus 2 because that's going to be the length of the bar minus the very ends, because we're going to exclude the endpoints because those are constant because we set them to 350 and 400. So, and then now we're going to want to put values for each of the 3 rows. So the first one is going to be equal to -r. And the second one is, oops, to 1 plus 2 times r. And then the third one is going to be the same as the first, and it's also going to be -r. So then those are your values for your 3 rows, because so ultimately we're turning the tri-diagonal matrix into abandoned matrix is what's happening. So we also need to identify this one, NP NX minus 2, which is the length of the bar, excluding the ends. And then this is the equation for plus, so this is everything but the ends. Times So there we go. This is technically the initial temperature profile. So, and then so we have to set each side equal to something. And so it's going to be your initial which these are going to be constant and staying the same, so that's why you have to have the plus R. 0. It's the same thing for -1. Oops. Okay. And then here we can graph the initial temperature profile. Very similar to the other. I can't type and talk at the same time, but it's very similar to the code from before regarding like the initial temperature profile. Okay, and then we can run this to check and see. Oh, I forgot an equal sign. Spelled that wrong. Okay, so here's the initial temperature profile. You can see the left-hand side, the initial temperature is 350 Kelvin, and then on the right-hand side, it's up to 400 Kelvin, and throughout the bar, the initial temperature is just 300. So that is correct for the initial temperature profile. So now we can go on and graph the rest of it. So for I in range, and do NT plus 1 in order to include everything. And then you can take this from here because we're going to need that. And then first, okay, before, well, yeah, you can do this first. So this is basically just solving your banded matrix. So solve underscore banded, and then you're going to have 1 and 1 because that's going to be your number of rows and columns, and then A, which is your banded matrix, and B, which is the right-hand side of your equation. And then you can copy stuff from before, and I don't think that just worked. I just undid that. That's not what I meant to do. That's fine. Okay, let's do it again. Underscore banded, and then 1, 1, A, B. Okay. Trying to make sure I didn't mess anything up. Okay. I think it's because I did copy select or cell first. I always do that whenever I try to copy and paste stuff. I always actually press the wrong thing. And then if I it's 5, we'll do 200 equals 0. And, ooh, that's an O. And then now we can graph it. So, okay. You do big equals big underscore subplots rows Well, actually, just kidding. You don't need to do that. X, Y, T, mode equals lines because we want to connect the dots. Name is going to be, oops, F, I, because we want it at the position that it's at. We don't just want the initial temperature profile, and then I don't think I need. And then fig dot show. Okay. Oh shoot, what did I do? Invalid syntax. No. Just have. What's wrong with that? Oh, I don't have a colon. I'm running into a lot of problems. Okay, here we go. So here you can see that this is very different from the last time when we used a value greater than 0.5, because at that time it was oscillating back and forth, so it was unstable. And now you can see here this is approaching more of a linear relationship here. So you can see that it's a lot more stable than the method we used previously. So the Crank-Nicolson method is valid for using any R value greater than 0.5. So yeah.